Hello, welcome to my live stream. Today we're gonna have a little bit of fun. We're gonna answer some questions, we're gonna write some code, and we're gonna learn as much as we can about interrupts. Let me know if there are any problems, if you can't hear me, if there's any issue, just write in chat, let me know please. If the music is too loud or anything like that. Alright, so let's start. In the last video we did a bit of great. I'm glad that it's crystal clear. In the last video in the last two videos actually, we worked on interrupts, and one of the main things was doing the hardware interrupts using the PIC chip. Now something I'd like to start with is to show you a bit how the Linux kernel looks like and how the implementation in Linux looks, and try to compare it a bit with our own implementation. And I think that would actually be very helpful to see how other people are doing this, how other people are writing drivers for this type of stuff. So I've got this. Yeah, so going into the Linux source, I found two places where this driver is implemented. There is this Arch x86 kernel i8259.c, and there's also this implementation from drivers. Now, they are almost the same, except that this one from drivers, it has some of the stuff, like these structures are a bit different, but the implementation is mostly the same. So let's take a quick look at what's dated here and try to compare it with our own implementation here. Okay, this is better. So here is our initialization code, and here is the initialization code from Linux. I'll make this a little bigger so you can see better. As you can see, they have this automatic end of interrupt given as a parameter. This pin lock, it's something. It's basically like a mutex, like a kernel mutex, so that this code only gets executed like one time. Oh, I'm really sorry. I forgot to switch to my... Okay, now you should see my screen. Okay. Alright, so as I mentioned, the automatic end of interrupt is given as a flag here, and they use this spin lock, which is like a mutex, so that this only gets executed like on a single thread. Okay. They start by masking all the interrupts. I mean, that's not a bad idea. And then they basically send... Okay, so here's the first difference. In Linux, they basically send all... They basically initialize the first PIC and then the second one. In our code, we basically interleaved those calls. So we are initializing both of them at the same time. They are using this 11, which means 1 and... Okay, so it's the same as in our code, the default settings. Okay, then they have this automatic end of interrupt here, and ICW for default. Let's see what that looks like. This one looks like the one we want to see. So it's set to 1, which means that they only set this 8086 flag, which I think is identical to what we did. And yeah, they also have this automatic end of interrupt. So they first initialized the first PIC and then the second one, so they are using basically the same commands. Yeah, now I mentioned in the video something that related to this IO wait, that Linux does something similar. If I go to the implementation of this outb PIC, we can see that it uses a delay. So this is basically a short delay. They are using timers instead of IO, but we don't have timers yet. We will implement them in the next video. Alright, so let's see what else is different. Now something something really interesting is this mask and acknowledge 8259. I'm not really sure why. This is something that I haven't figured out. Is when they handle the interrupts, they mask the interrupts and then they unmask them. I don't know why they do that. But here in this implementation, we also see something interesting, which is how they handle the spurious interrupts. So they are caching the interrupt mask. This is the one on the data port. So in our case, to modify the mask, we have to read what's on the data port and then modify it. But they are caching that value. And so first they are starting by doing a lightweight spurious IRQ detection, which, because reading from the PIC and interacting with the PIC is slow. I mean, this is a pretty slow device. That's one of the reasons why it's a legacy device. So they are checking if the interrupt line is masked, and if it is masked, then that means that it's a spurious interrupt. It's an interrupt that shouldn't happen. It wasn't disabled in the first place. Now, if it is not masked, then they are... we are looking at the Linux code right now. This IRQ real, I think it's in the same... Okay, so what this does is it reads the ISR register, the interrupt service... what was it called? Interrupt something... Interrupt request register, yeah. So it's basically the register which tells it which... for which interrupt there is a request pending, basically. And it's checking against that. Oh, and then... so this is also interesting. If you send this command to the PIC, then you will continuously read the ISR register if you read from the command port. So they are basically reading it and then switching back to the IRR or the... Okay, this is the... I made a little mistake. So the ISR is the in-service register, which means that it's the register which tells it which interrupts are currently being serviced by the CPU, and IRR is the register which says which requests are pending. So basically, which requests are waiting for us to finish handling this interrupt. All right. So then they read this IRQ real. So this function basically reads that and checks if that interrupt is in service or not, basically. And if it is not in service, then it means that it is a spurious interrupt and we have to discard it. But then the Linux code, so it has this if statement, and then at the end it does go to handle real RQ. So basically it does this all for nothing. It just counts the spurious interrupts and then handles them anyway, which I find pretty odd. This is pretty odd. I'm not sure if this... they don't even check. So that's what I was looking at. I was looking to see if they do this check like again when sending the acknowledge, but they don't. So that's interesting. That's a bit curious. So they're just logging a message, counting it. I mean, a high number of spurious interrupts indicates that there's noise on a line or some chip has failed, basically. And then it goes and handles it anyway, so... Alright. So, they also have this save, suspend, resume. Okay, I won't go too much into that. Then we have this probe function, which is also kind of interesting because as we write more drivers, we will want to integrate the APIC at a later point. So we will want to detect, okay, does this device support an APIC or not? Or does this device support an IRQ or not? Does this device have an PIC or not? So that's basically why we want to have these probe functions. And the way they are doing it is they're basically masking an interrupt. They are basically modifying the masked interrupts, and then checking if the value sticks, basically. So it's pretty easy to understand. All right, let's check the chat and see if there are any questions. All right, how can I wipe a corrupted Windows 7 and install Linux instead? Just put it on a live CD or a live USB and put it in a computer, just wipe everything. It should be pretty easy. Yeah, I mentioned that we are looking at the Linux code. Yeah, you're welcome. Okay, I think I responded this. All you have to do is just use like Berlin Etcher or Rufus or some other tool to create a USB drive with a Linux image, and just put it in your USB drive, reboot your computer. Maybe you have to press like F12 to go into the BIOS settings that control which device to boot, and that's basically it. All right. So what have we learned from this Linux implementation? And maybe there are some things that we want to integrate in our own operating system as well. Yeah, so caching the interrupt mask is a pretty good idea, so we don't have to read it all the time. At some point we will also have to do this to create spin locks so that we can now only execute these like in a single thread, like on a single CPU at the same time. And there are some more. All right, so let's go and let's go and improve our own interrupt, our PIC driver. All right, so how should we start? Yeah, so let's start by creating a mask for this mask, basically. Let's cache it as well. So I'll create a uint16 for the, and let's also make it static so it doesn't leak into other source files. Okay, and we will initialize it with FF. Basically, we want everything to be masked. And let's also do that first. So just mask everything. Or simpler, just call this disable function. Okay, and then once we initialize, it might also be a good idea to also call this disable function. So we basically mask everything. Now I'm not really happy with calling it disable. Let's do something else. Let's just call the mask and fine, I'll leave it. I was thinking to name it a bit different, but I think it's fine. Alright, so in disable, we also want to reset this mask, so alright. Um, yeah, something to... There are two PICs, so we should have a mask that has 16 bits, not just 8 bits. So yeah, FFFF, that would be the correct value for it. And same, when we disable it, we set it to FFFF. Actually, let's do something else. Let's just create a function. Set mask. Which just does this. Okay, so basically what I do here is I set the lower 8 bits to the first PIC and the upper 8 bits to the second PIC. And now all we have to do is just call set mask of FFFF, and I will do the same here because I think this makes more sense. Alright, now to mask a single IRQ, instead of having to read the mask, all we have to do is just okay, so let's extract it here. If we are on the first PIC, then it's mask equals the global mask and FF. And if we are using the second PIC, then the mask is the PIC mask shifted to the right by 8 positions. Okay, and we don't have to do this anymore. And oh, here's a little mistake that I did, because I should have set this to port, not to the PIC1 data port. Oops. Alright. And the same is gonna be for unmasking, except that instead of ORing, we are ending with the negated bit, basically. Alright. Alright, now let's also implement that end of interrupt, automatic end of interrupts, which is, I think it might be pretty useful. So I'm going to add it here. We need std int for .h for actually it's std bool, sorry, for boolean, and let's also store this. Alright, and we basically need to add the automatic end of interrupt if this automatic end of interrupt is set, then we will also add it to this fourth initialization control word. So PIC, ICW for end of interrupt. Now all we have to do is just set it here. All right, this looks pretty good. All right, now let's think a bit about how we can abstract this a bit. This is something that we will also want to do in the future with other devices. Now, for example, I don't really like this name, i686 PIC, because this is more like a specific implementation for the 8259. So I'm just gonna set modify this so it says what was the number? 8259. Okay, we've basically replaced it everywhere. Oh no. Okay, and I will also rename this file so it says i8250. Oh, I messed it up again, didn't I? Okay, and now pic.h is called i8259.h. Okay. Yeah, I added the automatic kind of interrupt flag here. Okay, I think that looks pretty good. Okay, so let's think about how can we create a driver out of this. Now, if we were in C++, then it would be very nice. We could create an interface for the PIC, and then have the specific implementations, like in our case, the 8259 PIC, just implement one of these interfaces. But we are in C, so we don't have interfaces and we don't have classes here. So how can we do that? And for that, what I will do is... okay, let's create it here first, and then I will think about where to put it later. So let's create a structure. And let's call this PIC driver. And this driver, it will contain a couple of methods, such as the end of interrupt. Now, this is really unpleasant because I have to do everything with function pointers. And this one gets the IRQ number. Okay, let's keep the code consistent. Then we will also have like a probe function, which will basically return a boolean telling if this this device exists or not. Enable and disable are also pretty important, so we will do those. Send end of interrupt, and then mask and unmask. I think these are the most common. Now, when we will actually implement the APIC, some of these may not actually work like this. They may have to be a little bit different, but at least we have a starting point that we can modify and change later, which is great. Okay, so yeah, masking and unmasking. Okay, so what I'm gonna do is I'm going to create an IRQ dot. I'm still gonna have like a PIC.h, which will contain this definition, basically. Because otherwise I would have put it in IRQ.h, but I don't want to introduce like a circular dependency between these two, so I'm keeping it here. Okay, so now instead of having the structure, I will include the other file, pic.h. And how can I do this? All right, so let's do like get driver, get 8259, get driver. And this will return a PIC driver instance. And we can basically delete everything, because everything will be done through this driver. Okay, now for the actual implementation. Okay, let's have a static and const PIC driver, which I wonder if we can do like okay. Okay, so let's see what we need to do here. Here, all we have to do is just return a pointer to this constant structure. And here, let's see how we can... I haven't implemented the probe method, let's also add that here. Okay, enable. Okay, so instead of enable, what I'm gonna do is just have the configure method here. Now something I'm thinking of is, because in the APIC we won't have these two offsets. Okay, let's add them for now, but in the future we might not have them. Okay, so now the initialize method is the i8259 configure. Disable is i8259 disable. Send end of interrupt is this one, send end of interrupt, mask and unmask. Alright, so now we have this PIC driver that we can use in the other places. Alright, let's quickly implement the probe, which should be pretty easy. So what we're gonna do is call, we'll basically disable everything. So I'm just gonna call disable. And then I will check okay, I will set the mask to, I don't know, some magic number like this. And yes, I should also implement a get mask because I don't have any. And all we have to do here is read from both of these. And the PIC one will be on the lower half, so return this, ORed with the second one, shift it to the left by 8 positions. Actually, we can just return true if the mask we've read is 1337. Yes, so that looks good. Alright, now let's see what else we have to do here. Okay, I think we're done with the PIC itself. Now let's see how we can handle this in irq.c. Okay, so what I will do here is I will include the 8259.h in here. And let's also have a static PIC driver. Which is initially null. And in the initialization method, what we will do is just go over all the drivers that we have. And then we will go over each driver to try to find one that exists. Okay, so if drivers of I probe, then we found our driver. I think I should create a macro for this because it's kind of annoying to do it all the time. Let's do that. Where should I put it? In... Alright, let's just go in util. Okay, so now we can go in irq.c, and I'm gonna include this util race and just use that size macro of drivers. And I think we can also mark this as const. Alright, so we found our driver, and if we haven't found any driver, it's not a bad idea to do some error handling here. We will print and here's a little idea. Let's also have like a const char name here that we can actually display. All right. And now we can initialize using this PIC driver that we found. So we'll print a nice message. Right, and then we'll call initialize using the remap offset that we have, and for now we will not be using the automatic end of interrupts. All right, then we register the ISR handlers, and then we enable the interrupt. Great. I will delete this. And at the end, all we have to do is just call the driver and tell it to send the end of interrupt. and I have to delete these. Okay, let's see if we can compile this code. Okay, we have some errors and warnings. Let's fix those. It doesn't seem to like my declarations. Is this how I have to do it? Yes. Okay, so more parentheses, because it's always fun to have as many parentheses as possible. And that's how you have interfaces in C, basically. It's kind of ugly, but it's the best way we can. I mean, Linux also does something similar, so. Alright, I implicit the declaration of function set mask. Let's try to fix that. In the 8259, I will move the set mask and get mask. Let's just move them up. Yeah, and now I'm seeing that I forgot something. Okay, so now that we have this set mask function, when we can use the cached versions. So basically all we have to do here is just modify the mask. Alright, and then we will call the... Actually, not even that. All we have to do is just call the set mask function with PIC mask, ORing this RQ. Now, I'm finding mistakes here and there, but not an issue, we can fix them. Alright, so masking, all we have to do is call the set mask function with the existing mask with the IRQ shifted by, with one shifted by IRQ bytes to the left. Alright, this looks good to me. Let me check if I made any other mistakes here. Yes, I think this looks pretty good. Alright, we'll fix all the errors. Okay, we should make this const as well. And the other cool thing about this is that we can basically delete everything from here. All we need is just this get driver function. We don't even need these anymore. Okay. We have some conflicting types for PIC driver in IRQ dot. Why could that be? Oh, I forgot the pragma ones. Almost there. Implicit declaration of printf. Okay, that should be an easy fix. stdio.h, and what else do we have? Assignment discards const qualifier. in IRQ initialize. So let's fix that as well. What? Oh, line 39, what? Oh, okay, so this one also has to be const. This looks... Okay, looks good. Okay, moment of truth. Let's see if this works. Hello from kernel. But yeah, basically all the interrupts are masked, so we want to unmask a couple just to see if they work. So let's unmask 0 and 1. These are the ones we use the most. And here we go. It works. Great. So, what do you think? Any questions so far? Is it clear what I'm doing here? Is this interesting or... Yeah, this is great. So we've basically refactored a bit the code in our PIC. Now we have this actual driver, which kind of works like an interface, but in C, because in C we don't have interfaces, we don't have classes, we don't have any such thing. Alright, I wonder why isn't that printf showing? I haven't seen it, which is kind of odd. I'm expecting to see this printf. Maybe I just didn't notice it. Ah, okay, so it's just because I'm doing like a clear screen right before this hello from kernel. I think that's the reason. Okay, so that looks good. Alright, now this is basically what I had in what I kind of wanted to do today in this live stream, but we have plenty of time left, so yeah, I'd like to hear from you what should I work on next? What should I explain next? What should... Alright, if I think we should commit this code because it's pretty good. So I will Sound Blaster 16. Yeah, that's a bit more advanced topic. That's but I can take a look and maybe give you some hints if you want to do it yourself. Okay. And push, and now you should have all this code. Okay, let's see this suggestion, the Sound Blaster 16. Let's figure it out. My first idea would be to try to look up an article on OS Dev, because those are usually pretty good. And here we go. Okay, so you are looking at the PIC bus. This is a prerequisite, basically. In order to get information about which ports, you basically need to read the PIC information. And the PCI information. And you can do that by reading from this configuration space here, basically. this article kind of goes into a lot of details on how to do that. Yeah, I would say this is a bit more advanced topic, but it's definitely something that we will want to do at some point. There's a lot here. There's a lot of information. But basically, you don't need to implement like all of it. What you need to do is just try to find the information on how to detect the device that you want. And once you detect it, there's also ACPI, which is the Advanced Configuration and Power Interface. But yeah, this is a bit of a more advanced topic. I think it's easier to just do this. Use the PCI to get information about what devices you have, what their ports are. This is gonna give you a lot of details about that. And basically, using the device ID and the vendor ID, you can identify which device this is. And you can probably find lists of device IDs online. And the Sound Blaster, I don't know what this one has, I have no idea, but yeah, you should probably look for some documentation, which would be pretty useful. Now, this Sound Blaster 16 is also supported on ISA cards. ISA is the precursor of PCI. So today you have PCI, PCI Express, a lot of, and these basically kind of work similarly, but PCI Express has some extra stuff, whatever. The idea is that ISA is the older standard, and this is kind of, I mean, it's very old. It's like from 80s, 90s, early 90s, basically. So there's no point in trying to implement that. Yeah. You can probably find... okay, that's interesting. So it looks like... another idea on how to detect the Sound Blaster 16 is to just poke around using these ports, which are usually pretty standard. Yeah, you could do that instead. And here you have plenty of information about how to interface with this driver. Oh, and it uses DMA, which is also another pretty old, very old technology here. But yeah, it kind of works on any computer, any emulated computer, which is why it's great. Alright, another suggestion was to talk about the keyboard. I won't go into this today because I want to make a separate video about that. I want to make a dedicated video because there is a bit of complexity to that topic, so I think that, but I can show you some pointers. So basically, you are gonna be using, you don't need any PCI stuff, you don't need any ACPI. This is a very simple device. I think it's port 80 or 60 in hexadecimal, if I remember correctly, from a long time ago. Where is it? I can't find it. Okay, so the main idea here is that you initialize the device. There are these commands which can help you do that, and you have to pick a scan code set. Basically, there are 3 scan code sets. I think the first one appeared on the original IBM PC, the second one on the IBM PC AT. So what the scan code set is basically a mapping from a physical key to a number. And you can find tables of these scan codes online. Yeah, here you go, scan code set 1. Basically here you have a table with what each scan code, what key it corresponds to. There are some differences in how they work. For example, in some scan codes, basically, if you press and then release, there are separate scan codes for each, like the upper bit, for example, the most significant bit usually, and nothing if you press it, basically. So you have to check for that bit. In other scan codes, you have like another special scan code that's sent in front of it. All right. Okay, so basically that's the main idea, and then you will want to have your own mapping of these scan codes in the actual driver. When you handle the keyboard interrupt, you basically just have to read all the scan codes and then process them. And usually what you have to do is put them like in a queue, and then have some other code that, for example, wants to read from the keyboard, have that code just poll that queue and see when there's something new and read it from that queue. You don't want to use the interrupt handler as an event handler. That's not how it should work. The interrupt handler, you should exit from it as soon as possible, because interrupt handlers basically block code from executing. If you have multiple threads running, then your code will be stuck in that interrupt handler instead of doing some other more meaningful work. So you want to have these as light as possible. Alright. If there are no more suggestions, then I have two options. One of them is to try to make some improvements to the bootloader. I have plenty of ideas on how to do that. The second idea would be to do some graphics, maybe. Is there anyone curious about how to do that? I've experimented a bit with it. It's not code that I will make a video at some point about this subject. I will 100% make dedicated videos about it, because it's a complicated and very interesting topic. But at this point, we can try to play around with it a bit, see how we can basically change the video mode. And does that sound interesting? Would you like to see that? Okay. Yes, okay, so people want to see the graphics. Great. Okay, so what I'm gonna do is I'm gonna quickly go over the hardware side. Oh, what we have to know about. So the standard is called VBE. Alright, so basically what we have to do here is communicate with the BIOS. So these VESA functions are implemented in the BIOS. If we are using UEFI, then we have access to GOP, which is much better and easier to use and to set up. But in our case, we are using this legacy boot mode, so we have to use the BIOS and these VESA functions. Now, there are a couple of functions here available. Get controller info is basically how you can probe to see if the VESA extensions are available on the machine, and if you can switch modes. Then you have this get mode info, where you basically iterate over a couple of modes and you pick the one which looks good to you, which is closest to what you want. And here is some code which shows you how you can basically do that, but I will try to implement that in just a moment. And there are some common mistakes here that we should know about. Okay. Okay, let me just open my experiment that I did a while ago. Okay, so some time ago I did some experiments with graphics, and I just want to see which one is it, because I don't remember. Okay, make... Okay, so it's probably not this one. Maybe not this one either. I'm not really sure which one it is. Okay, it's not this one. Not this one. Yes, this is the one. All right, I found it. So I have a reference source code when writing this, so I can explain better. And I won't look like such a fool. Okay. So basically, what we have to do is start going in stage 2. That's where we will start, and all right, I'm just gonna open my reference really quickly. Okay, so first things first, we have to basically collect that, call that get controller info. That's the first step. Okay, so let's try to implement this structure. Okay, I will start by creating a VBE.c and .h. And we basically have to create this structure. There is no point in doing this manually. Just gonna copy and paste, because that's our favorite thing as programmers to do. Okay, and we will need for uint16, we need stdint.h, and our function will just do okay, so this one has a return code that we can return, and get VB get controller info, and we will store that in one of these structures. Okay. Okay, I think it might be a good idea to look up some documentation about this stuff. So let's do that. So basically we are looking at that Rolf Brown interrupt list. And we are looking for interrupt 10 and for F00 basically, and we want to know what it contains. Come on, 10 for F00. Okay, so this is basically the BIOS function that we need to call, which will give us all this information. Okay, I want to use the actual name. All right, this looks good. So now let's see how we can implement this. What's wrong? Struct. Yeah, I should have put this in VBE.h. All right, and now we will implement this function. Okay, now there's not much I can do here because I basically need to go into this x86 ASM and always calling BIOS functions is very fun. So let's just call video get VB info. And it will return an integer. And we will just wrap this. All right. I don't remember how I handled the pointers. Okay, so I do the pointer conversion from protected mode pointers like linear pointers to the segment and offset scheme. I do it in assembly, so that's what I wanted to check. Okay, so all we have to do now is implement this function. Global. Okay, and I will just copy the code from this grid because it's very similar. I enter real mode. I will have to save the modified registers, and at the end I have to enter protected mode and then do the rest. And this is this push EX and pop EX is so that I can save and restore the return value, because this enter protected mode will change the value of EAX. All right. Now let's see how to implement this enter real mode function. This is gonna be the fun part. Okay, so we can actually look at this example code from here. There's some example here where they basically alright, so there's not much to it. All we have to do is just call int 10 hexadecimal, set AX to this value, and then ES to the segment of this pointer, and DI to the offset. That's basically all. We have a macro for getting that segment and offset. So linear to seg offset, BP plus, let me think about this, plus 8 I think should be. So we have the 32-bit return value, which is 4 bytes, and then we have this EPB, which is another 4 bytes. So it's BP plus 8, and we want to store it in ES and DI. Now the way this macro works is we have to use the extended register of EDI. We have to get bit as a parameter here. And now we have in ES the segment, in DI the offset. And what is left is to set AX to this number. And int 10 hexadecimal. Okay, and then we have to check that it returns 004F. We basically handle that in the C code, so I don't have to do anything here. Since it's already in AX, then we have to do nothing because AX contains the return value. Alright, so it might be a good idea to clear EAX because I'm not sure what the value of that is. So that's it. Alright. Okay, let's see what we get. Yeah, and the reason why I wanted to look at this documentation is to see this table here, because this is not enough. Alright, so what we have here is the signature. We already have that. Then we have the VBE version, the VESA version number, then a pointer to the OEM name, whatever, capabilities and flags, then another D word of... Okay, so this is a pointer to a list of supported VESA and OEM video modes. Okay, so this will contain basically the list of video modes that we will look at. And total amount of video memory in 64K blocks. Then here, this is the part that I wanted to show you, is that we need to reserve 236 bytes. Alright. In VBE version 2 we also have a couple of extra things, but I don't think any of these are any useful. And then after these 236 bytes, we will also have another 256 bytes OEM scratchpad or whatever. Alright, so basically what we need to do is reserve a lot of memory here and make sure that it's not filled with something else. Alright, so we will reserve 236 plus another 256. Okay. What is wrong? What? Okay, it's just being weird. Okay, something we can do here is just have this as a boolean, and we have to include std bool.h, because we don't really care what the return value is. All we want to know is if it worked or not. So, and here in the documentation we can check that. Return. So AL should be 4F and AH should be the status. So basically what we need to have here is to just make sure that this equals 004F. It's basically the reverse of the function 4F00. Alright, there's nothing else that we need to know here, just if it worked or not. Okay, let's try this and see what happens. Let's see if we can build. Yes, we can. Let's go to main. We will not execute the kernel. All we... Okay, let's include VBE.h. Okay, and now we need to get one of these info blocks. Now, the way we handled memory in the bootloader in stage 2 was just these defines. We need to find an area which is free. I don't know. Okay, so starting from address 30000, it's free. So let's reserve that as memory VESA info. Alright, and just want to convert this to a pointer. Okay, and then we will get the controller info. And now let's print some information. Okay. Now let's run and see if we can... no VBE extensions. I think that might actually be an issue with how I am running the image. Let me check. It's not that. I wonder what it could be. Maybe I'm doing something wrong. I do remember that there was a bug in this x86.asm code. This enter protected mode function. In some VBE implementations, the bug is that they will reset, they will enter protected mode themselves, so they will basically reset some things. Let me check. In entry.asm. Alright, this is where we are entering protected mode. The 820 line will remain enabled, so this is not something we have to worry about, but what we do have to worry about is this GDT. Because if the VBE code, the BIOS implementation of VBE enters protected mode, then it will overwrite our GDT, so we have to basically set it again. Let's see where I do this. Alright. I have to make it global so I can access it from x86.asm. Let's see if this will work. Now, obviously, this code is very hackish, what I'm doing here. And let's try to call this before going back into protected mode. So call load GDT, and let's see if this works. Yep, it works. Okay, so that wasn't the issue, but there's definitely an issue. So let's see what it is. Let's actually see what this returns, because I have no idea. What I will do is just let's print this. Okay, so I'm just getting 0. That's odd. Let me see if I did something wrong, because it should not return 0. But yeah, I mean, it could return 0 if this doesn't exist. Which is odd, because I tested this and it worked, so what could be wrong? I don't know. Let me see if I did something different in my implementation. Okay. Get controller info. Yeah, should work. I have no idea. Okay, it might be a good idea to save some registers here before calling this. Let's just do a push A, and then actually no, this will modify the. Okay, I'm just gonna push the ones that we modify. So EDI, ES, and EBP is modified by in some cases the interrupt will modify EBP, so we want to make sure it's unchanged, and then we can pop them. But it's probably I'm not sure if I doubt it's this, which is kind of odd. Okay, let's try to debug. Let's see if box works or not. Oh, damn it. Display library WX is not available. Box is not very happy. I don't know, I've had a ton of issues with box. Maybe I don't have. Okay, I do have box X, so let's try that one. Debug. Okay, box config. And let's try to use X for graphics. Okay, so this works. Okay, no extension here either. Let me see if there's some option that I need to set for box. Okay, so I'm using this VGA ROM image, Okay, so this is the option that I need to set for box. VGA extension VBE. Let's see if that works. To give us anything. No VBE extensions. Okay, so I'm definitely doing something wrong. I'm not sure what. Okay, I'm gonna implement it the way I did it earlier. Maybe... Okay, here's my other implementation. I'm not sure what I'm doing different because it looks pretty much the same to me. Other than the fact that I'm checking this for F value here. And I'm just returning -1, so that's the only difference. Okay, it should work. I mean, it's basically the same. Which is why I find this strange. Okay, fine. I'll just do it this way. Maybe AX changes, but that's odd. Why would it change if I already push it and then pop it? Anyway. Fine, I'll just copy this. Seriously, what the hell? VB extensions. Okay, let's check. What else to check? I don't know. I mean, this would work. I don't know why it's not working. Alright, let's just do a diff. So I'm gonna use meld and see what is different. Okay, bootloader stage 2 x86.asm, and let's compare that with the one that I know works. Where is it? Compare. That should not affect anything. Okay, so what the hell? Oh, okay, so it just combined a lot of functions into one. Okay, so I'm calling int 10 hexadecimal and then I'm checking the return. And the rest should be the same. Okay, let me try something else. Maybe it's this memory address, it doesn't like it. Let me see what I set it in the other one. Okay, so I'm just using a different address, but everything else should be the same. Fine, I'll just use 40,000. No controller info. Seriously. It's odd that it's returning 0. Okay. Let me try something else. So debugging works, alright? Let's try to debug this. So the way I set this up is that I have the stage2.map. So let's see where this function is. So let's... Okay, so it should be at 1F6A. We're gonna go to disassemble at 1F6A. And I'm gonna double click and now click continue. And now it should break when it enters this VBE get controller info function. Okay, so let's go step by step. Okay, here is the call to the assembly function. Okay, so first I am going to push, I'm gonna save the call frame, and then I have this enter real mode. Okay. What is this code? Oh, damn it. Yeah. If it starts with FFF, then something's gone wrong here. If it starts with FFF, it's basically in the BIOS, but it's not in the BIOS. That's odd. Okay, I'm gonna reset. Okay, so here we are switching to real mode, so we should be in the enter real mode macro. We are right here, so we change CR0 and then we do this far jump into real mode. And now we are in real mode, and we reset AX DSSS and re-enable interrupts. Alright, so now we should go back to this push EDI here. Okay, then push ES. And now, oh, something is odd. Dereferencing a null selector. Something is wrong with that. That should not be happening. Because we should... Okay, we are in real mode. Ah, damn it. I'll reset. Okay, switching to real mode. Okay, I moved too fast. Let me try again. Yeah, you need patience when doing this. A lot of time. Okay, so once we enable interrupts, then we may get interrupted at any time, which is a bit annoying. Okay, so what I'm gonna do is just set a breakpoint, for example, here where I have this move AX. Okay, so now we are setting AX to this value. Then there's this linear to segment offset macro, and we should end up here. All right, so now let's see what we have. So ES is what? 3000. This is correct. DI is 0, so 30,000 is to write it in segment and offset. You basically, the easiest way is to put to divide the number by 16 to remove basically the last digit and have that last digit be the offset. That's the easiest way, and this is how I did it here. All right. Oh, and here it is. EAX is 4F00. So what the hell? Why does it change? That's the odd thing. Okay, we got another interrupt. Damn it! These are annoying. Okay. Okay, so now we are comparing AL to 4F and AL. It did not work. Okay, I will reset again because something doesn't make sense to me. Something doesn't add up. Alright, so I just want to jump to this int 10 hexadecimal and continue. Okay, so AL should be 0, but it should not. No, AL should be 4F, but it's not. Okay, maybe there's an issue with the BIOS image, because that's an issue I've seen before with Box. So I'm gonna use the same image that I used in my other, but Camo is very odd to me because it should work. Camo should work, which is the odd thing here. Okay, let's try to see if there's an option to set. Okay, VBE support. It should theoretically support VBE 2.0. Okay, so let's try this flag here and see if that's what we need. No VB extensions. Okay, I'm gonna try this VG ROM image and see if that solves the issue. box. No VBE extensions again. This is very strange. Okay, here it is. It's actually VJ BIOS call. Return VBE info ES3000 DI0 IX4F00. It finds the video modes. So technically it should work. I am stupid. I think that's... Let me check, but I think I did something stupid here, which is why it didn't work. So here, if AL is 4F, then I go to error. Okay, so I set EAX to -1. No, I'm not that stupid. Yeah, I thought that maybe I did something wrong here. Maybe it should return 0 when it works, but apparently not. Okay. Am I... Alright, let's try again. Okay, maybe this works. Let me see. Kernel.map. Maybe something. Stage2.map. Video get VB info, it's at 76E. 76E. Continue, and I will put a breakpoint at this int instruction and go one step further. Okay, so it worked this time. You can see that EAX is this, and AL is 4F, which means it worked. AH is 0, which means that this worked. So what am I doing wrong then? Okay, it's gone into another interrupt. What if I do this? I force this to be 32-bit. Okay, so the way I implemented this before is so that I can do... Okay, so EAX should have the status. Okay. And -1 if there's an error. Okay, that's great. So this means that this works. So if this is 0, then it's all good. Alright, this took me a while to figure out, but it was working. Because if there's an error, then EAX should be set to -1. So yeah, leave this as an integer. Okay, so we have... Oh, come on. Now what? Oh, return. Yeah, that was it. Found VBE extensions. Great, finally. Finally it worked. Okay, now let's continue and try to implement the next method. Okay. Something else we could do here is convert that. Okay, so let me show you what I want to do now. Okay, now this video mode PTR, the BIOS will basically set this to an segment and offset. I don't like having two 16-bit numbers. Okay, so I'm just gonna have a 32-bit number, which is the video mode pointer, and this is a pointer to where these video modes are stored. Okay, and what we have to do here is convert it from segment and offset to a linear address. So info video mode PTR equals I don't know, do I already have something like that? Maybe in memory? Nope. Okay, so how do we do that? Basically we have to multiply the segment by okay, the segment is basically the upper 16 bits. So we have seg of shifted to the right by 16, and that will give us the segment. And to get the offset, we just need to mask the upper 16 bits. So we will do this. Alright, and now to convert from segment offset to linear, we have to get the segment of seg off shifted to the left by 4 bits, so basically multiplied by 16, to which we add the offset plus the offset of seg off. Okay, this isn't the prettiest macro, but it is what it is. I mean, we're hacking away here. I include memory.h. Alright, so let's see. Identifier of is undefined. Oh. Okay. That should look good. And we will return true, otherwise return false. Does this work with Camel? Found VB extensions. I don't know. I did something wrong here when checking that return value, I guess. And now it works. Okay. Now let's go back to main. And now we want to iterate over these video modes. So we will have VB. Okay, so it's basically a 16-bit pointer array. Mode, which we will set to 16t, pointer of info video mode PTR. And now we will iterate until mode becomes 0. Okay. Okay, let me check how these modes are stored, because if I remember correctly, okay, so while modes is different than FFFF, we basically get the next. Okay, so all we're doing here is just iterating over these. So I could do the same. Int e equals 0, mode of I is different than FFFF and I++. And let's just print what modes we get. All right. Okay, quite a lot of modes. That's great. Okay, now let's see how we can obtain more information about these modes. For that, it's basically the same procedure. This time we call the get mode info function, and for that we need this gigantic structure here. Very consistent OS dev. Okay, whatever. I'm not gonna bother changing the... this is just a hackish implementation, basically. Alright, so we will have this structure. Which is the VBE mode info. And now we have to add _t to all of these, which is kind of annoying. Okay, I think I'm done. Okay, one more. Okay, and let's do the same. VB get mode info. And this one will have two parameters. The first one will be the mode, and then we'll get the VB mode info. And I will just do the same, except that, yeah, there will be other pointers to convert. There's the linear frame buffer. Okay, this frame buffer. This is basically gonna contain the... Actually, this might not be in segment and offset. Yeah, this is not in segment and offset. Definitely not. There might be some other stuff that's segment and offset, but whatever. Let's... Okay, get mode info and 16t mode. All right, and let's just call the right function mode info of mode and info. Okay. And now in assembly, I'm just gonna copy the code for the get VB info because I know it works. And what we have to change is, let's see here. We're basically calling for F01. Okay, so what we have to set is CX should contain the video mode. And another difference is that yeah, okay, so this will be plus 12. Move ECX or CX, actually it doesn't matter, BP plus 8. So the arguments are pushed in reverse order. Yes, so the first one will be the first argument, the leftmost argument. So this one is plus 8 and this one is plus 12. Okay. Then we are calling interrupt for F01 and the return is probably the same. Yes. No, it's not the same. It's the same. AL is for if this function is supported and AH is 0 if it is successful. All right. That looks good. Anything else that I missed? I don't think so. All right. Next we have to go to main and we will allocate some more memory. Let's just call this mode info and I'll use address 5000, 50,000 or whatever in hexadecimal that is. Okay, so get mode info of mode of I and then mode info. Okay, let's just not have that many ifs here, nested ifs. Right. And now we should have continue. And let's print some information about this mode. Okay, I'm just gonna reuse this printf. Okay, so what we are interested in is basically the resolution, the bits per pixel, and whether it has a linear frame buffer or not. Okay, so let's do that. Width, height, bits per pixel, and I think to check for the frame buffer there's a flag. Let me just check here. Okay, so it's inside this attributes. All right, so it has that 90 flag, then that means it has a frame buffer. But actually, I don't even care about that. Let's just print whatever is in that number. Frame buffer. Okay, and then the frame buffer. And let's, okay, there's some issue. Video get VB info. Okay, I think I forgot to rename. Yep. All right, and here we go. So these are all the resolutions supported by the video card, not the monitor. Something to note here. If you read here in common mistakes, this is not the monitor information. To actually read the monitor information, there's a whole different standard, and it's actually pretty complicated. It is called this EDID, and it's a huge thing that basically needs parsing. There's a lot of information there. You basically need to parse it. There's another call, there's for F15, which allows you to read the EDID data. This is basically the information that received from the monitor. And yeah, there are a lot of fields here, and if you want more information about that, basically you have to read this VESA EDID specification, or just try to find some parser and integrate it into your OS. Maybe it's not worth trying to figure out how to parse that stuff. All right. So let's pick a video mode. 1024 by 768 or whatever. Sounds good. Now, this algorithm of picking the video mode, you might want to do something like, I don't know, picking the closest match. But what I'm going to do here is just desired with, and let's set that at 1024, desired height 768, desired BBP 32. And we'll just search for a mode that has all of these things. So if all of these things match, basically. With height and BPP. Okay, there's no point in printing this information anymore. All right, and let's just have an uint16t picked mode. Break from this for loop. Okay. So the next step is to check if picked mode is different than FFFF, then it means we found our mode. But if it... Okay, and the next step is to basically switch to that mode. That will be the next function that we will implement. Let's see, which one is it? 4F. Okay, it's 4F02, set video mode. And what we need to provide it is with the for F02 in AX, and BX should contain the video mode. And then for VB3+, the CRTC information block, whatever, we don't care about that, we'll just set them to null, both of them. Alright. Okay, let's start from assembly this time. Just gonna copy this get VB mode info again. set mode. All right. All we need is the mode in BX. So move BX BP plus 8. Yeah, something I forgot, I think, here is to save CX. This is just to avoid issues later. And then restore. Okay, so set video mode. We're not gonna modify EB. Actually, okay, ES and DI we will modify. And maybe EBP because the box VB changes the EBP value. And also BX. Alright, and at the end we will pop EBX. Okay, and the interrupt is AX4F02. BX should have the video mode, and then we just call it and then check the return, which is the same as before, so nothing to be changed there. Okay, now let's try to change the video mode. Okay, so yeah, I have to implement it here first. Now, the reason why I'm implementing this VB.H and VB.C is that to kind of abstract the x86 calls, these BIOS calls. You've seen, for example, here I want to convert from segment and offsets to linear. It's easier to do this in C than in assembly. And you know, that's kind of the main reason why I did this. Okay, set mode, and all we need is the mode. Oh, and I forgot something to clear ES and DI here. I remember that. So, okay, before doing this, let's do move AX0, move ES AX, and move the EDI 0. Okay, so make sure it's null. Okay, yeah, next let's create a declaration, the definition here. Set mode. Okay, and now we are in VBE.C. Set mode and ensure that this returns 0. Okay. All right, then let's go back to main. Okay, we'll just call set mode of picked mode. And let's see if this works. Yes, it works. As you can see, we've got a blank screen here. Okay, now the question is, how do we draw something to the screen? And the answer is we use this frame buffer. So let's just create a new int8 pointer called frame buffer. Actually, since we have set the BPP to 32, we can do 32-bit colors. So let's just, I think it might be easier. All right. And we're interested in the frame buffer. Frame buffer from the mode infrastructure. And I don't know, let's set this to something. I'm too lazy to write all of this. And I think I should start iterating using the height. Okay. Okay, so we are basically iterating by both x and y, and we are gonna set frame buffer of y multiplied by the mode info which one was it? Let me see. I think pitch. Let me check. Because basically, there might be some padding bytes here and there, so you can't just use the width and height. Let me check here if there's any information on OS Dev. Okay, here it is. So number of bytes between lines. Okay, so offset, the beginning of the line is line number multiplied by bytes per line. So I don't know how it's called. All right, let's see. Bytes per line, which one are you? Okay, number of bytes per horizontal line, it's the pitch. Weird names. Okay, back to main. Plus x equals a color, and now to determine which pixel format you have to use this, but we're just gonna write something to see some pretty colors. So let's write I don't know, x plus y. Let's see what we get. Let's see if we get some pretty colors. Okay, so we've written the first row but not the other ones. Why is that? Oh, it's not plus, it's multiplied by mode info pitch. Sorry about that. Alright, and now we have some colors. Whatever color is this? Let's try some other colors, I don't know. Okay, so basically it looks like the blue is the lower 8 bits is the blue component. Now I'm not really sure what color format it uses, but okay, let's actually figure it out. I'll define a macro RGB, and so we've seen that blue is the lowest bit, so I'm just gonna do B. Okay, let's assume that green is the middle and red is the higher part. Let's see if that works. Okay, so we've shifted green by 8 bits and red by 16 bits. If I am correct, then doing this of 25500 should give us a red screen. Yes, it is red. Something is odd here. There are these blank lines in between, which is something a bit strange. I'm not really sure. Okay, I think I know what the problem is. So FB is a unit 16T, so everything I do here I have to divide by 4. And now it should be fully read. Yes, that was the reason. Okay, so let's see if the B component is working. Our screen should be green now. And 255 for B. And now we have blue. Yay, we have colors. We have pretty colors. Alright, so let's just mess around and do some pretty colors. X plus Y. Let's see what we get. There we go. Here we go, colors. And we can actually write, we have graphics now, which is great. So basically what we want to do is pass this frame buffer to the operating system and also pass this mode info so that the kernel knows how to draw. It knows all the details about the video mode that's currently on. Now this for example, this color format here, I guessed it, because it may not be BGR, it may be something else. So you kind of have to look into what all of these fields mean. For example, red position and red mask, that will give you how to write red. Green position and green mask will give you how to write green, basically. And since you're using, you know how bits per pixel you have, then you will probably know how many bits per color you have. Actually, yeah, so yeah, using these three, you determine how to convert that color from RGB to whatever format is used by this. Alright, so this is basically a quick introduction to graphics. I've shown you how you can do graphics. Now it's up to you to actually draw something pretty to the screen, because that's the biggest amount of work. It's a lot of work, and the reason why I'm not doing it in the main series right now is because I want to get the basics done first. We are trying to write a kernel here. If we do graphics, then we probably want to have at least 2 read files, so we can print bitmaps. We want to read fonts, so we basically need to have a file system already working, and a couple of other things that should work, basically, to properly do graphics. Because, I mean, I could introduce graphics now, but you're not going to be able to print text to the screen, which, I mean, printing text to the screen is like one of the most basic debugging features. I'm planning to do a video soon about how to do serial debugging. Not serial debugging as in serial printing. So basically using the serial port to print debug messages. And that's going to be a very useful feature to have, because on your main screen, even now, once your screen scrolls and you can't see the text anymore, then you're out of luck. What if the error you're trying to find has already passed? It's flown up. That's the main issue there. So for that reason, you basically want to have serial, outputting stuff through the serial port. Outputting debugging information through the serial port is going to be extremely useful. Also, when you want to do graphics, maybe something doesn't work and you don't know what, and outputting debugging stuff through the serial port will help with that. Okay, we are closing to the end. If there are any more questions, okay, someone asks, okay, I'm just gonna show you a bit Okay, some suggestions on how to get that fixed. I'm not really sure what I did wrong. I definitely did something wrong, but I finally fixed it. Now, I won't publish this code on the main GitHub repository. I'm gonna create another repository and post it there. Maybe in that experiments, I have a Nanobyte OS experiments repository. I will put it there if you wanna take this code and play around with it. Alright, questions, and then we will end the stream. Where did you learn to code and for how long? So I've started to learn in middle school. We had some C++, I think, or Pascal actually. No, I started with Pascal, which was fun in the 6th grade, and then with C in like the 7th grade, I think. But I didn't understand a lot of concepts. In the 9th grade, I basically started experimenting with, a quick history lesson. Back then, it was in 2000, around 2007, 2008, approximately, when I was in middle school. And we didn't actually have modern compilers. We were using Borland C++ or Turbo C++, also is also another name for it, which looks like this. It is very fun. But something that I discovered was, I started experimenting with all kinds of different things, trying to basically learn how to code. And I found that this compiler had a pretty extensive help. Let me see if there's any pictures of that. I don't really see any right now, but yeah, the help in Turbo C++ was actually great. It was awesome. There was documentation for everything. There's this conio.h file which contains some console stuff. And that's basically where I found how to change colors on the screen, and that was very fun. And then at some point I started experimenting with mode 13H, PJ mode, and there's this very nice course that still exists today about VGA basics, and this is basically how I did it. I didn't know anything about what this code meant. I just copied it and pasted it, and it changed the screen. It changed the video mode to this video mode, and then I could change the colors by writing to address B8000, I think. Okay, it's A000. So there you go, and you have 256 colors that you can play with. Here's how to plot a pixel. And yeah, I had a lot of fun with this and was experimenting with this. This will only work in Turbo C. You basically have to use, nowadays you have to use DOSBox to be able to run it, because I mean it's MS-DOS. It's a DOS program. I was limited by 640 kilobytes of memory, so that was a big issue for me because I wanted to do double buffering, and I couldn't fit everything in memory. I mean, I could fit a full buffer in memory, but then I couldn't fill like something else because it used a lot of space. That was fun. Yeah, it's cool. I mean, you can do a lot of stuff with this. And I kind of started experimenting, how to print fonts. I learned how to decode a BMP image without compression, without any advanced stuff. So just a very plain indexed color. Also another thing, because I learned how to convert to the indexed color in Photoshop. and I could basically make an image look just like I wanted using the indexed colors. I also learned, I started, trying to figure out how to implement like an UI, how to do fonts. Of course, my fonts were just bitmaps, fixed width fonts. So, but yeah, it was a fun time. Then in high school, yeah, I mostly learned by myself. At school, we did like we had a computer science class, which, but it was mainly focused on algorithms. Yeah, we had a lot of fun, and also in high school we also used this thing, so you can imagine how far behind is like the school the school system, the education system here. And I think right about when I was in like the 10th or 11th grade, they started switching to using code blocks with MinGW. Yeah, and then in the 11th grade I started learning by myself C#, which was also very cool. I loved to do all kinds of projects. And then university. In university you learn a lot. You learn about a lot of technologies, you learn... For me, university was more like an introductory course about what is out there. And it kind of taught me how to learn things and how to approach learning and how to search information, how to find information about all of these topics. And it also introduced me to the topics themselves. This is how I learned that, how to design compilers and how to, I also had a lesson about operating systems and how they work. We didn't actually write an operating system, which was kind of unfortunate, but I did it for fun at some point. Yeah, and then I've been working in the industry for the last, so I finished university in 2015, I think. Yeah, in 2015 I finished university, and since then I've been working in the industry on various projects, various technologies. Even right now I have a project where we have everything. We have Java, we have .NET, we have C++, we even have low-level stuff. So you learn a lot, and there are things that you learn from experience. That's how I'm able to do things so quickly here. I just look up some information and I quickly do it, because having that experience really helps. And this is kind of what I'm trying to teach here. I'm trying to focus a lot of my videos on how to learn and where to find the information. If you noticed my style, how I do the videos, I always explain, okay, this is where I found this information, this is where I found this information. Okay, let's think logically how to find that information. So that's the main idea. Okay, are there any more questions? Let me check. Okay. Yeah, I agree. Implementing stuff before graphics. There are some more important things. There's memory management that we definitely need to get right. There's the scheduling, task scheduling. That's a very important one. The main recommendation is to not do graphics in the kernel. I mean, seriously. Maybe have some primitives in the kernel, like, I don't know, having a way to create like a virtual frame buffer that the application can just write into, and then I don't know, integrate it with some display server that will take that and put it into Windows and all that. But yeah, these are some things that you need before you can... I mean, you can do things in any order that you want, but this is the order that makes most sense to me. And maybe it might make some more sense to you as well. I really want to be as good as you. You will be, Illusion Game. You will be. One day you will be. Trust me. You keep doing what you're doing, learn, and you will get there. Yeah, free Pascal. I think back then I used Turbo Pascal as well, because that was the MS-DOS thing. Is free Pascal on MS-DOS, or is it like 32-bit? I have no idea. Okay, so it apparently supports 32-bit as well. Okay, I haven't really used Pascal in a long time, and I don't even know how it works anymore. I do remember that you have to type begin and end for everything, but yeah, I haven't used it in a very long time. Now, for operating system development, free Pascal is actually pretty nice because it has it supports classes, and it's low level enough that you can do a lot of things that are harder to do in higher level languages. So yeah, it's a good language for doing system development. Actually, the original system, the old Mac operating system, what was it called? System 8 or something like that. It was written in Pascal. So yeah, there's some history for you. Okay, so if there are no more questions, we will end the stream here. I hope you enjoyed it. Thank you a lot for watching, and we'll see you in the next stream. The plan is to do these live streams more regularly. I'm thinking maybe every 2 weeks or something like that. But I will see later. Okay, 2 new things. How to play sound from a headphone jack with assembly only. Basically, to play sound you need a audio driver. One of the simplest ones is obviously the Sound Blaster 16. It's one of the simplest to use and most universally supported by a lot of hardware. You can also use the PC speaker, that's the easiest one. But yeah, it's very limited. You can. Okay, let's see. OS Dev. So, to make sounds out of the PC speaker, all you have to do is just use this code. You can do it in assembly using the outb instruction, basically. You can actually do this in 32-bit code as well, so you can integrate it in your kernel and do all kinds of beeps while doing stuff, if you want to do that. This is actually just using the programmable interrupt timer. The PIT has a couple of channels, and you're basically using channel 2, I think, or channel 3, something like that. And you're writing the frequency, and the PIT, the programmable interrupt timer, will basically generate, will take care of basically controlling that sound device and sending it the samples. So you don't have to do, you only have to call display sound, have a delay for a couple of, I don't know, a second or two, and then call no sound to mute it. That's how you do, that's the easiest way to do sound. 64-bit, I don't know when I'm gonna do 64-bit. I wanted to do it earlier, but I kind of want to get the basics done first, and then we will take on 64 bits, we will take on UEFI, and a lot more stuff. Okay, so okay, the stream cut out for a few seconds. Sorry about that. For user space, yeah, you basically need to implement the tasking mechanism. Yeah, there are a few more things that you need for that. Yeah, we'll cover it in a later video, user space. Okay, if there are no more questions, then we will end the stream here. thank you again, thank you a lot for watching, and we will see you the next time. Okay, have a nice evening, and goodbye.